So right now we're going to talk about the electromagnetic interaction. And if you guys have ever played with magnets, you probably know a little bit about the subject. Whenever you take two sides of a magnet that don't want to stick together and you try to push them together, you're going to feel a force that's going to be pushing them apart. It's a repulsive force. Now in electricity, that's going to happen anytime you have a positive charge with another positive charge and you try to stick those together. They're just going to repel. The closer you hold them, the harder they're going to push apart. Same thing with negatives. So if you have a negative charge and hold that close to another negative charge and you try to push those together, they're going to repel as well. The closer you push them, the harder they're going to push apart. Now if we do just the opposite, say we take a positive and a negative charge and we try to push those together, we can imagine what happens. They like each other. So general rule for this, opposite charges, they're going to attract, while like charges, they're going to repel. Like charges don't like each other. Okay? So keeping that as a general rule, this is something that people studied since way back when, but they couldn't really figure out. And it's only recently that we kind of discovered how to control this force. So it was Coulomb who was able to quantify this force with an equation. I'm going to write F with a little E next to it, say the electromagnetic force. He said whenever you have two charges, and we'll represent those charges with Q's, say big Q and little q, a big charge and a little charge, and you multiply it by some constant, we'll say that's Ke as one constant, you can divide that by the distance squared between them. Now if you guys have watched the video about gravity, you're going to notice this is the exact same ratio as gravity. It's kind of weird. The only thing that's different about it is whenever you have charges, it doesn't really need to be positive and positive, or positive and negative, or negative and negative. It doesn't matter what charge you have. This is just going to measure the force that's either pulling them together or pushing them apart. So an example of this, say I had these spheres, and we'll say this distance is the exact same between them, okay? Say this up here was a +2, and this was a +2, and this is a +2, and this is a -2. So looking at what would happen with the top spheres, we know they're going to repel each other. And at the bottom, we know they're going to come together. And they're going to come together with a certain force. We could plug it into this equation and figure out, but I'm not going to do that right now. So what this is actually measuring, though, is just either the repulsive or the attractive force. So the number that's going to come out here is going to be the same when you take its absolute value. So whenever you're trying to figure out the force between different charged objects, a good idea would actually be just ignore the signs, ignore whether it's positive and negative. Whenever you're plugging it into this equation, you're only looking for magnitude. So they might ask you a couple of questions like, say I have +4, say I have a -1, and say I have a +4, and say I have a +4. Don't be confused at whether it's going to go together or whether it's going to go apart. Whenever you're measuring the force, it just doesn't really matter. These are going to go together, sure, but they're going to go together with a certain attractive force. Whenever I measure the repulsive force of this guy, it's actually going to go apart harder. So even though this is coming together, it doesn't mean that this is a greater force than this. So you just go by the quantity of the charge. That's the important thing to remember. So another thing I wanted to talk about regarding electricity is the study of like currents, etc. Whenever you're looking at an atom, and this is something you guys will learn in a later unit, there's a bunch of different models. We could say one of them, it's going to show protons and neutrons and electrons all as parts of a single atom. And what they are, protons, those are just positive charges that exist inside of a nucleus, or inside of the center of an atom. The electrons, those are going to be negative charges that kind of swarm around the nucleus, we could say, for right now. So you guys have probably seen pictures like this in your textbooks from high school or elementary or whatever. That just shows that there is a separation of charges inside of an atom. Now this is going to cause a whole bunch of different things. For example, friction or contact force. Whenever I put something, let's say I'm putting my hand up against the chalkboard, I can push, but whenever we're thinking about this force, I have electrons and I have protons in my hand, and the chalkboard, that has protons and electrons in itself. So whenever I'm pushing, what I notice is that my hand, it stops at a certain point. Now whenever it stops, what's actually happening, my hand isn't really touching the chalkboard per se. It's just getting really, really, really close. But the electrons that are in the atoms in my hand, those are actually repelling the electrons that are in the atoms in the chalkboard. So it's just like the magnets. Whenever I get closer and closer and closer, they're going to push apart harder and harder and harder. and we just don't notice it because it's so small. We feel like we're actually touching it. We actually feel the pressure from the chalkboard. That's actually just the repulsion from the electrons in the chalkboard on the electrons in the atoms in our hand. So whenever we're touching things, whenever we feel friction, whenever we feel a contact force or something like that, we're really just feeling the electromagnetic force. Now another cool thing, whenever we study the atom a little bit, we figure out that these electrons, they're outside of the nucleus. They're kind of on the outskirts of the atom, we could say. And some of these guys, they can actually leave the atom. They can kind of move over to other atoms if they want. And this is especially true in metals. If I have, for example, a copper wire, copper, we'll say that's one of our elements with a bunch of electrons. Some of those electrons, they're going to be allowed to leave their nucleus to go swim around other copper atoms. So if I have a wire, and I'm drawing it like super big right now, the electrons in this side, because they don't have to stick around their nucleus, they can swim around to the other side just fine. Now that's where we get current. So if I was able to, let's say, get a battery, something that can send charges through, we'll say this side's positive, this side's negative. I can send a wire through to be able to drive a current through like a light bulb. So that's kind of how electricity works. Whenever we find something, some sort of substance that allows electrons to travel through it, we call that a conductor. Now metals, they're very good conductors. Copper is a very good conductor. We can think about that because we use copper in like everything that has to do with electricity. Versus if we have something else, like let's say I have rubber, either rubber or salt or something like that. And whenever I say salt, I mean salt in a solid form, okay, like a big old block of salt. If I have one of these and say I try to drive a current through it, if I try to pass electrons through it, nothing would happen. It doesn't like to do that. So if I tried to shoot electrons through here, it would just kind of stop. So there's some substances that don't allow electrons to swim through it like copper does. Those substances, we call them insulators. So there's a difference we just learned there. There's conductors and there's insulators. Anyway, as far as electromagnetic force goes, I think the most important thing to know regarding the test would be this equation, be able to plug things into it, be able to understand what it means, and be able to apply it with pictures of like spheres like this. Just give yourself maybe different combinations, say, +4, -2, just make stuff up, and compare it against two other spheres, and put them at different distances and see what happens. And you can make up numbers, it doesn't really matter. You can make up different numbers. Just go ahead and test yourself to see if you can come up with a force after plugging it into this equation. When I say you make up numbers, you don't have to have anything in specific for anything, including that constant. So whenever you're practicing this equation, I would recommend just sub KE in for 1. So you could just plug 1 in as the constant, and it doesn't really matter. But you still get an idea of what the ratio is. It's the same as practicing like the gravitational force.